we'll start today with a little bit of revision from the previous class. I want to start with a small question, right? So I will give you a few compounds here, and I want you to tell me the oxidation number of each of the atoms in all of these compounds. So we'll start with that, and then we'll move on to the next part, which is reactions, or we are going to observe a type of reactions called redox reactions today. So we'll talk about redox reactions afterwards. So first, write down a small question. Give the oxidation number of all the atoms of compounds below. Give the oxidation numbers of all the atoms. Of the compounds below. Quickly get this done. I'll give you 2 minutes. This wouldn't take 2 minutes even. Are we done? I believe by now you would have finished. So let's discuss. Now, can someone tell me the oxidation state of phosphorus here? Now I have just briefly written X here. I will do the calculations and show. What is the oxidation state of phosphorus here? +5. +5. Very good. So let's see. Hydrogens are +1. Oxygens are -2, and then you write, if you write the equation here, +1 plus x minus 2 is equal to 0. So then we have x minus 1, because when they solve it will be x minus 1. Sorry students, bear with me, I just completely didn't write the number of atoms of each of these. That is wrong. So we have plus 1 multiplied by 3, and x here, plus there are 4 oxygens, so therefore 4 multiplied by minus 2. Each oxygen is minus 2 in charge. Each oxygen is minus 2 in charge. So therefore when you write this, it should be equal to 0, the overall charge of this molecule or ion. So since it's a molecule, there is no charge. If all of the oxidation numbers are added like this, it should be equal to 0. So we have plus 3 plus x. Now 4 into minus 2 is going to be minus 8 is equal to 0. That means x minus 5 equals 0. X is equal to plus 5. Now you don't have to show all of these workings like so. You can actually calculate it and get to the answer on your own without having to show the rest of the calculation. If you understood this, then you can directly get to the plus 5 oxidation state later. And if I move on to the next one, can someone tell me the oxidation state of sulfur here? Plus 6, correct. So again, this is plus 1, this is minus 2. There's only one hydrogen, so I just write plus 1. There's only one sulfur, plus x. And there are 4 oxygens. So 4 multiplied by minus 2. Each oxygen is minus 2. This is equal to 0. So then plus 1 plus x minus 8 is equal to, not actually 0, this is equal to minus 1, the charge over here is equal to minus 1. The charge over here is minus 1. So therefore we have x minus 7 is equal to minus 1. So when you send the minus 7 to the other side, it will be minus 1 plus 7, which is going to be plus 6. X is plus 6, that is correct. And finally we have this. Now you have to be careful with this. Nitrogen, we don't know the oxidation state. Oxygen is minus 2. So we have 2 nitrogens. So therefore 2x. 2 nitrogens is 2x. Plus 1 oxygen. So we can just say 1 multiplied by minus 2 is equal to the charge. There's 0 charge here. So that means x or 2x minus 2 equals 0. 2x minus 2 equals 0. That means 2x equals plus 2, x equals plus 1. Did all of you get to plus 1? Right. Can you remember, I told you this is the most commonly used method to figure out the oxidation number of atoms. But I also mentioned in certain cases it gets us to slightly incorrect answers, right? That is, like, if one nitrogen is 0 oxidation state, we wouldn't see it here, right? You have to draw the structure and see. Do you understand? So in this case also, in this particular case, all the rest is correct. In this case, actually the 2 nitrogen atoms that are here in N2O does not have the same oxidation number. Both nitrogens does not have the same oxidation number. So therefore both nitrogens are not actually plus 1 oxidation state. Slightly different to that. So what I want you to do now is to figure out the actual oxidation number of both the nitrogen atoms, right? Can you draw the most stable Lewis structure you can draw for N2O first, and then find the oxidation number there on each nitrogen atom quickly? So this is revision, otherwise you wouldn't remember how to do these things. So try your best to get to the answers as fast as possible. I will stop at this point. Quickly get to the rest, please. Some of you are done? Done? Very good, very good. So yeah, that's the level that I want you to be at, right? If you are done by now, that's really good. Can someone tell me the oxidation state of, oxidation state of nitrogens, like two different nitrogens are there. In the sense, nitrogens with two different oxidation numbers are there. Can someone tell me what those are? Any values on the two nitrogens? +2, -2, and the other one? -1. Right, so nitrogen -2. Let's see. Okay, we have to see other answers. +2. Nitrogen. Both nitrogens or one? One. What about the other one? No charge. 0. Okay, we have few answers. Shall we double check quickly? Students, now pay attention. Guys, now this is Lewis structures. You should be able to draw Lewis structures. I don't suppose that, like, Lewis structures is difficult. It's like you have to blindly follow the steps. Right, like when it comes to Lewis structures, drawing Lewis structures is, I wouldn't say a difficult task, because you have to follow steps. Following steps is what is required of you when it comes to drawing Lewis structures. Now you have to be thinking logically as well, right? Sometimes, like when it comes to converting lone pairs into bond pairs, you have to think logically, but mostly it is obtained through following of the correct steps. So if you take a look at nitrogen here, or N2O here, nitrogen is the less electronegative element. Oxygen is higher in electronegativity than nitrogen. So nitrogen will be the central atom, right? So that means central atom is nitrogen, and to the central atom we have an oxygen connected on one side, a nitrogen connected to the other side, right? So as a central atom you have to choose nitrogen first. After that, since we have used two bond electron pairs, so now I had to represent altogether 8 electron pairs. I have already used 2 electron pairs as bond electron pairs, so I'm going to remove that from here. Then I'm left with 6 electron pairs. Now I have to distribute 6 electron pairs in this structure. We always start with the most electronegative element first. That means the outside elements, the most electronegative ones. So there are 2. There are nitrogen and oxygen. Out of these 2, which one is more electronegative? Nitrogen. So therefore, students, we will be starting with nitrogen. 1, 2, 3. And then now octet of nitrogen is complete. Oxygen. We are starting with oxygen. So oxygen's octet is now complete. You have 2 electrons here and 6 electrons around it. 2 plus 6 is 8. Octet is completed. So we are now moving on to the outside nitrogen. The central atom gets electrons last. So we put the electrons, the remaining 3 electron pairs, onto nitrogens. So this is how we will add electrons here, right? We had 3 remaining. We added them on this outside nitrogen, not the central one. Central one, we don't add electrons initially. If we have any remaining after adding electrons to the peripheral atoms or the atoms that are on the outside, If you have any remaining only, we will give it to central atom. Clear? So these rules are in your head. So now we take a look at the charges. So if you take a look at the charges, you can say oxygen should have valence electrons 6, right? So oxygen has altogether here 6 electrons. Apart from that, in this bond, 1 electron belongs to oxygen, right? A bond is formed with nitrogen's electrons and oxygen's electrons. So 1 electron is oxygen's. So therefore oxygen has altogether 6 plus 7 electrons. So 6 plus 1, which is 7 electrons. 6 plus 1, which is 7 electrons. Right? So basically this electron on the bond plus this 6. Right? So basically oxygen now has 7 electrons. Oxygen has only 6 valence electrons. It has 1 greater or 1 1 electron more. So therefore the charge over here is 1 minus. Okay, having an additional electron will cause oxygen to have a formal charge of 1 minus. This nitrogen, usually nitrogens come with 5 valence electrons. So therefore students, let's see whether nitrogen has 5 valence electrons. We can very clearly see there are 3 lone pairs. So now there itself it has 6 electrons, and in this bond 1 electron belongs to this nitrogen. 1 electron belongs to this nitrogen. So therefore altogether 7 electrons are there. 7 is 2 greater than 5, right? So that means when it comes to nitrogen over here, it has 2 more electrons additionally taken. So therefore the charge over here is 2 minus. The nitrogen over here again should have 5 electrons, but it actually has only 2 electrons. 1 electron in this bond and another electron in this bond. Right, only 2 electrons. That means it is missing 3 electrons here. So therefore this has a plus 3 charge. This is absurd, no? Can't have charges separated like this. This is very weird. That is wrong. So what we do is we convert lone pairs of either oxygen or nitrogen to bond pairs. Now when you are doing this, we have to keep in mind, after the conversion of lone pairs to bond pairs, the more electronegative element should still be carrying a negative charge if there is a negative charge in the negative formal charge in the molecule. Is that clear? If there is a formal charge in the molecule, if it has a negative formal charge, it should be on a more electronegative element. So that means oxygen should be carrying it here if there is a formal negative charge. So students, converting lone pairs of oxygen is not wise. We can convert lone pairs of nitrogen into bond pairs. Is that clear? So what we do is we convert 1 lone pair of nitrogen into a bond pair. So let's do that. When you do that, what happens? This nitrogen is losing an electron, so therefore it goes from -2 to -1. Now this nitrogen now has 1, 2, 3 valence electrons. So it is missing only 2 valence electrons. So +3 becomes +2. Right? In other words, when a lone pair is converted to a bond pair, this nitrogen atom is losing an electron, this one is gaining electron. That is the case when it comes to whenever we convert a lone pair to a bond pair, that is what is happening. Again, still too high of charges are present, so we convert another lone pair of nitrogen to a bond pair. When you do this, this nitrogen loses the electron, so minus is gone. This nitrogen gains the electron, so this +2 is gone. So we have +1. Is that clear? Can I convert this lone pair also here? No. Why can't we? Because nitrogen can't have more than 4 bonds. So this is the most stable Lewis structure. You can draw other ones and then we can talk about resonance structures, but I asked you to draw the most stable Lewis structure. This is the most stable Lewis structure. Is that clear? Therefore students, if you take a look at it, you can see this oxygen is, if you see how the bonds are polarized, oxygen is more electronegative than nitrogen. So therefore this particular bond is polarized. The bond electrons are more attracted towards oxygen. So therefore in this bond, this side is -1, this side is +1. Is that clear? So therefore overall charge on oxygen would be -1 here, -1 here, altogether -2. +1 here, +1 here, altogether +2. Is that clear? Do you understand? Right, so this is how you will write the charges. And what about this nitrogen? Any of these nitrogen bonds, are they polarized? No. So therefore this nitrogen would be in zero oxidation state. Is that clear? Do you understand? But when we calculated it this way, we got a +1. That is the averaged out value. Averaged out value. Is that clear? That means if you take this oxidation state and this oxidation state, add them together, divide by 2, you get to +1. Is that clear? So that is what we have actually obtained in the previous case. Now you know the actual scenario. Take this down if you haven't actually gotten to this answer. Okay everyone, so now we are done with, this was just a small revision to get you up to speed. We need to remember these things. But I told you, when it comes to finding the oxidation number of an atom in a molecule or ion, we use this easier method, and in certain cases, in certain specific questions, they expect you to draw the Lewis structure and get to the answer, but most of the time we use just the calculation based method to get to the oxidation number of different atoms. Is that clear? There are very specific instances like the ones that I just showed you, like N2O, S2O3, where we get to with these different answers. Okay? Right, so now we are moving on to a new topic, redox equations. Redox reactions. Redox reactions. Now, redox reactions are quite simple, students. Redox reactions talk about the fact that if you have a chemical reaction where something is losing electrons while the other reactant is gaining electrons, there is obviously an oxidation and a reduction happening. Right? For example, if you take sodium, this is something very familiar to you. If you react it with chlorine, you can actually form sodium chloride. Sodium chloride. This is not balanced. I will teach you how to balance a redox reaction as well. So redox equation balancing is taught at 2 levels in this lesson. Right? Today I am not going to go into detail at all about redox equation balancing. Today I am going to make way for the much advanced version of redox equation balancing that will be that we will learn later. Today we are just setting the stage for it. We are trying to understand the basic concept of redox reactions. Right? So after that, right, much later, maybe on the 4th week, we will be learning about redox equations, proper balancing of redox equations. So today, after we learn a little bit about redox equations here, we are going to move on to naming compounds. Okay? So keep that in mind. So I told you this is not balanced. Now you yourself can balance this. Like in O levels you have done this, no? How would you balance it? There's 2 chlorines here, 1 chlorine here, so you write 2 here. Right? And then you have 2 sodiums here. To balance 2 sodiums, you would write 2 here. That's the way you would do it. Right? That's another way of balancing. We'll be learning it in a second. So before we move on into that, you have to understand, here we have sodium. Here we have sodium in a compound. This is sodium element. This is sodium in a compound. Here we have chlorine element. Here chlorine in a compound. 2 different things. So now tell me, what is the oxidation state of sodium when it is present as an element? What is the oxidation state of sodium when it is present as an element? What is it? Plus 1 or plus 2 or 0? 0. Elements will always have 0 oxidation state. So this is also an element, this is also having 0 oxidation state. Now this sodium, you know this is an ionic compound, right? So what is the oxidation state of sodium in ionic compound, or any compound for that matter? What is the oxidation state of group 1 metals in any compound? Plus 1. Every single compound that group 1 element is present in, except for hydrogen actually, any group 1 metal in a compound will always have plus 1 oxidation state. So this is plus 1. What about the oxidation state of chlorine then? Minus 1. If sodium is plus 1, another one has to be minus 1 for it to be neutral. Right? So what has happened here? Sodium has increased in oxidation number, 0 to plus 1. Increase in oxidation number is referred to as oxidation, while chlorine has decreased in oxidation number. This is referred to as a reduction. This is referred to as a reduction. Okay? So, whenever in a chemical reaction, if there is oxidation taking place, there is always a reduction also taking place. Oxidation taking place means there is something in the reaction is undergoing reduction, because if I am giving out electrons, there should be someone taking electrons. I can't keep giving out electrons and not have anyone take it. Is that clear? If a reactant is oxidizing, giving electrons away, there should be another reactant that is gaining the electrons, right? So the main thing here is the amount of electrons given off by a reactant should be exactly the same to the number of electrons that are taken in by the other reactant. Is that clear? So in other words, there can't be a mismatch in electrons. Number of electrons removed, number of electrons gained should be the same. That otherwise that chemical reaction is not necessarily happening the way we have written it, right? So for example, over here, if you write when it comes to sodium, these are called half equations. These are called half equations. So I will write oxidation half equation. Over here, sodium is the one that is getting oxidized. Sodium is becoming sodium 1 plus, removing an electron. And we have chlorine that is undergoing reduction. Chlorine, it is present as a molecule. It will be taking electrons in to become chloride ions. Now students, there are 2 chlorine atoms. So for one chlorine atom to form a chloride ion, it needs to take 1 electron. Chlorine atom is neutral. Chloride means additional electron is there. It is 1 minus. Chlorine atom is neutral. Chloride ion or Cl1 minus ion has 1 additional electron. That means it has to gain 1 electron. Now here there are 2 chlorine atoms in a molecule. So how many electrons should it gain? 2 electrons. How many chloride ions would it form? 2 chloride ions. Okay. So that means students, if you were to consider this particular reaction, oxidation, it releases 1 electron, but this guy takes 2 electrons. That means if I am going to balance this equation, I need to multiply this oxidation reaction by 2. Then only the number of electrons that are removed then only the number of electrons that are removed matches the number of electrons that are taken in. Otherwise, electrons that are given off does not match the electrons that are taken in. 1 electron given off, 2 electrons taken in, doesn't match. So therefore students, we need to keep in mind before we add them together, we can multiply this by 2, right? If I multiply this by 2, right, separately, I don't want to erase that, but here I'll multiply it here itself. Then the electron numbers, they match. Okay, so then if you add them together, you can see the electrons, they cancel off, right? These electrons, they cancel off these electrons. That's another thing you need to keep in mind. When it comes to half equations, you can add them together. Half equations, you can add them together. If you have the same thing on two different sides of the arrows, on the left hand side you have same thing, as well as on the right hand side also you have the same thing, you can cancel them off. Is that clear? So here on the right hand side you have 2 electrons, here on the left hand side you have 2 electrons. If I am going to add these together, these 2 electrons can be cancelled off. So then the equation would become 2 sodium plus 1 Cl2 turns into 2 sodium ions and 2 chloride ions. Now students, 2 sodium ions and 2 chloride ions means what? Chloride and sodium, they join together when they are present as ions. What is it? Sodium chloride. How many sodium chlorides do they form? 2 sodium chloride. Is that clear? Sodium ions and chloride ions, they attract and form sodium chloride. Right? 2 sodium ions means 2 sodium ions joining with 2 chloride ions will form 2 sodium chloride. So therefore, if I am balancing this equation, I need to write 2 in front here, nothing here, and 2 in front here. That's it. Is that clear? So this balancing came through a redox balancing method. You could have looked at it and balanced as well, but later on, much later on in this lesson, we learn about other types of redox reactions that are difficult to balance by looking at this side and looking at this side. Okay, that's not going to be possible. So therefore you have to use this type of balancing method. Is that clear? Right. So this is just somewhat extra for the time being for you to get into your heads that there is an electron transfer happening. So what is the electron transfer that happened? 2 electrons given off, 2 electrons taken in. Okay. So now copy this down under redox reactions. But take a redox reaction heading first. I will tell you, I will give you a small sentence and then you can take it down. Write a small heading. You can write down. When a chemical reaction shows both an oxidation as well as a reduction, when a chemical reaction shows both an oxidation as well as a reduction, they are categorized as redox reactions. So as the whole word redox is made up of, you can see the red ox, red stands for reduction, ox stands for oxidation. The word red ox stands for reduction and oxidation. Okay. So categorized under redox reactions. If each individual oxidation reaction, and reduction reaction, oxidation and reduction reaction is written separately, they are known as half equations. They are known as half equations. If each individual oxidation reaction and reduction reaction is written separately, they are known as half equations. They are known as half equations. Okay, students. Now you can take this down. First, please take this equation along with this oxidation and reduction part, and then write the half equations. Then write the half equations. Please do that. I'll do one more example, and after that I expect you to be able to get to the answers for the next two questions I'll be doing with you. So we'll do one more question. Now, let's see. If you take, these are reactions that I want you to develop an idea on, right? So now, this one I will do it step by step very clearly, so for you to understand how to approach a question like this. So now let's say we have aluminium reacting with chlorine. Aluminium reacting with chlorine. Forming aluminium chloride, AlCl3. Now let's write the oxidation numbers. Aluminium is an element, no positive or negative oxidation numbers are not seen here, it's zero oxidation state. And aluminium here is present in a compound. Now students, aluminium is a metal that always forms +3 charged ions. Or even if you didn't know that, under the rules we studied, we realized, or we mentioned, halogens are usually -1 in charge, unless they are connected to a more electronegative element than themselves, right? So chlorine is always -1, except for when it is connected to a more electronegative element. Now, if chlorine is connected to more electronegative like fluorine, chlorine becomes +1. If chlorine is connected to more electronegative like element like something like oxygen, oxygen is also more electronegative than chlorine, then what happens? Chlorine becomes +1. Except for those, every other instance chlorine is usually -1. We mentioned that last week under the rules. So this is -1. So you can find out the oxidation state of aluminium, right? X plus -1 into 3 equals 0. That means X plus -3 equals 0, right? So that means X is equal to +3. So X, in the sense aluminium is equal to +3. Is that clear? So now chlorine has become -1, which is a reduction. Aluminium has become +3, which is an oxidation. Okay. So I want you to balance this. But when you're balancing, you have to do it mindfully. Mindful. You have to think about it and do it, right? So let's say half equations. Now keep in mind, students, this is the tip of the iceberg, okay? The half equation part that I'm teaching you today. I'm not going into deep, like, proper half equation theories or calculations. Actually, the theory remains the same, the calculations are going to be different. So that will come much later. So today you will develop an understanding of what half equations are. Is that clear? And then we'll learn, like, really good exciting reactions much later. Actually, don't think that I'm, like, saying exciting because I want you to think this is very interesting. No, actually, if you are studying chemistry and then you have to face A-levels, one of the main things that you will struggle with in the future is balancing equations and figuring out what happens when you're looking at the equation. Now imagine that problem was not there for you. when you look at the equation, you figure out, this is what happens. This is what could happen if you connect this with this, right? So you don't have to memorize too much. So then, like, the burden you have will be gone. So that's why I say the future of this lesson is actually going to make your life a little bit easier. It will be interesting. Okay. So over here we have aluminium oxidizing. So if I write the oxidation half equation, it's going to be aluminium turning into aluminium 3 plus. So to produce aluminium 3 plus, how many electrons should I lose? Obviously 3 electrons. And we have reduction half equation. Now I'll number this equation, okay? I'll say this equation is equation number 1. Then we have reduction, we have chlorine becoming Cl1 minus. We know it has to take 2 electrons. So therefore this is going to be 2 Cl1 minus. This is the reduction. So that is, let's say, equation number 2. Now if I'm going to add these together, I can't. Why? The number of electrons that are taken in is different to the number of electrons given out. So, or in other words, the reaction number 1 has 3 electrons here, reaction number 2 has 2 electrons here. They don't match. How do you make them match? We can multiply them with different numbers, right? What is the best number to multiply the reaction 1 with? 2, right? Then this electron number will be 6. What is the best number to multiply reaction 2 with? 3. This will be 6 then, right? So basically, if there's 3 electrons here, you multiply this with the smallest even number, and you multiply this with the smallest odd number you can think of other than 1, right? So that is 3. So if you multiply this by 2, multiply this by 3, both are getting to 6. Is that clear? So if I write it here, 1 multiplied by 2, you don't have to actually show this step, okay? Now I'm teaching you, so I have to show this step. And when you're learning first, you have to write this step as well. But in the future, you can omit this step, directly get to the final answer if you have enough experience. Meaning, the step that I'm writing now, you can do it in your head. You don't have to do it written down like this. So anyway, the first one has to be multiplied by 2, so that means 2 aluminiums become 2 Al3 plus and 6 electrons. And then we have, I will write it here itself, right? 1 multiplied by 2 plus 2 multiplied by 3. Second reaction multiplied by 3. I will write it here, so then I can add them together very nicely, right? Second reaction multiplied by 3 will be 6 electrons plus 3Cl2 turns into 6Cl1 minus. If you add them together, it becomes, you can see electrons cancel off. So we have 2Al plus 3Cl2 turns into 2 aluminium 3 plus and 6 Cl1 minus. So this actually means aluminiums and chlorides together will form aluminium chloride. Okay, so this is going to be 2 aluminium chlorides. Is it understood? Okay. Take it down, students. Now gaseous state aluminium chloride is a different story. We don't talk about it here, but I just want you to take this down and develop an idea about what is happening here. You can write a new question. Write the reduction and oxidation half equations. Write the reduction and oxidation half equations of the following reactions, and balance the equation. Basically like this. Now I balance this equation. I now have 2 here, 3 here and 2 here. I have balanced the equation. Is that clear? So I'm expecting you to do the same with the following questions. So question number 1 is magnesium reacting with oxygen turning into magnesium oxide. Reaction 2, we have iron Fe reacting with oxygen to form Fe2O3. Can you please balance this? I want you to do the same. Do the same as we have done here. Write the equation, identify the oxidation numbers, figure out which is oxidizing, figure out which is reducing, and then write the half equations. Right? If you are advanced enough to eliminate this step, go ahead. I don't have a problem. Shall we discuss? Right? So let's do the first one. Okay? First one, you can very clearly see if you write the oxidation numbers, oxygen is getting to a low oxidation number of -2, so it's a reduction. Magnesium is increasing in oxidation number, so it's oxidation. This is oxidation, this is a reduction. Now students, if you write the equations, you can very clearly see magnesium becomes magnesium 2 plus, releasing 2 electrons, because you can see it's +2 oxidation state. Oxygen is becoming oxide, right? -2 state oxygen, O2 minus oxide, right? Group 16 elements, when they are forming ions, they will gain 2 electrons and form 2 minus ions, or oxide, or O2 minus ion. So now students, that means each oxygen atom should gain 2 electrons to form 2 minus charged ions. One oxygen atom, like if you just write an oxygen atom, it is the one that is turning into O2 minus, no? That means there should be 2 electrons that is gained to turn into this. But the thing is, we have 2 oxygen atoms forming O2. So that means we need to have 4 electrons forming, given to O2 molecule to form 2 oxide ions. Is that clear? So the oxygen molecule should be gaining 4 electrons altogether. Did you recognize that part? Did you understand this part? Is that clear now? Right? Okay. Then you form this. So now we can just basically you can identify there's 4 electrons here, 2 electrons here, not a match, meaning what? We need to multiply the reaction number 1 by 2, and then to that we will be adding reaction number 2. Is that clear? So that means if you do that, you will get 2 magnesium plus O2 turning into 2 magnesium plus O2, because this is 2 here. This also becomes 2, this becomes 4. They cancel off. I just omitted the part that I said you can omit if you like. Right? So I just wrote the answer without writing the half equations again. So the answer becomes magnesium 2 plus, there are 2 of them, plus 2 O2 minuses. Or else you can just write magnesium oxide 2 as well. 2 magnesium oxide, because if they are added together, if these 2 are added together, you are getting magnesium oxide, 2 of them. Is that clear? You can do that as well. Okay. If you write the next equation is this. I said Fe plus O2 turns to Fe2O3. Right? Did you get to the numbers? Can someone tell me what goes in front of Fe? What is the number that goes in front of Fe? 2? 2. What about this one? Now I'm asking, after balancing it, after completely balancing it, what should be the number that goes here? 4. 4 and this 3. 4 and 3. Anyone else? For this, what is the number? 3. For this, what is the number? 2. Right, so you are getting different answers, right? Two different students are getting different answers, right? So we'll see what happens, right? So now first of all, let's identify which one is oxidizing, which one is reducing. We have Fe, which is 0. This is also 0. What about this? What about this? What is the oxidation state of Fe here? That you have to figure out. Oxygen is always -2. Oxygen is always -2 in a compound, right? What is the oxidation state here? +3. Correct. Very good. Right? So now this is undergoing a reduction. This is undergoing a oxidation. We understood up to that point? No problem? Right. Then I will write this half equations. For oxidation, it's an easy one. We have Fe turning into Fe3 plus. Why did I write 3 plus? +3 oxidation state. Is that clear? Fe is at +3 oxidation state. So what is the charge on Fe then? 3 plus. Is that clear? This is an ionic compound. And then 3 electrons are removed. That's why it forms 3 plus. So we'll call this reaction number 1. Reduction 1, if you write the reduction equation, I want to save some space, that's why I'm writing them close by, close together actually. Let me bring them in a bit closer. Reduction. So reduction reaction, what is happening? Again we have O2 turning into oxygen 2 negative or 2 minus oxidation state. Right, so again, to make one of these, one oxygen ion or oxide ion, it needs to take 2 electrons. There are 2 oxygen atoms here. So how many electrons should we give? 4 electrons. You need to understand this very clearly. If you don't get that part, that is problem. Is that clear? One oxygen atom requires 2 electrons. In an oxygen molecule, you have 2 oxygen atoms, so it requires 4 electrons to form 2 oxide ions. So this is our second reaction. So the electrons do not match. Electrons do not match. So what do we do now? Can we do something about it? Let's see. If we multiply this by 2, this gets to 6. Can we get this to 6? No. So the next even number is, now we have to multiply this by even numbers, right? If you multiply this by 3, you get to 9. Can this even number ever get to 9? No, right? So therefore we multiply this again with another even number. So what is the next closest even number to 2? 4, right? Or else you can just use your brains, like, how can we get these two numbers to be the same? Yeah? This one multiplied by 4, this one multiplied by 3. Right? You just multiply them by their, these numbers that are found in front of them. So if you multiply this by 3, you get to, sorry, this by 4, you get to 12. If you multiply this by 3, you get to 12. So the number of electrons become 12 on either part, so on each side. So therefore, if I write first reaction multiplied by 4 added with the second reaction multiplied by 3, then at that point we have this situation. We have 4Fe turning into 4Fe3 plus. I was planning on eliminating this, but since we have a large number of electrons, I thought I'll write it. And then the second reaction multiplied by 3 would be 12 electrons plus 3O2 turns to 3. Oh, actually I haven't written the correct number here. This was 2 earlier, so when it is multiplied by 3, it becomes 6 O2 minus, right? So if you add them together, you can see 12 electrons here and 12 electrons here cancel off. So that means 4Fe plus 3O2 becomes 4Fe3 plus and 6O2 minus. Fe3 plus with O2 minus forms Fe2O3, right? So how many Fe2O3s can be formed here? 2 Fe2O3s. 2 Fe2O3s. I'll write that down. So you can write the final equation like this. 4Fe plus 3O2 turns into 2 Fe2O3. You can write it like that. I normally indicate it like this. No, some of you might be wondering, shouldn't we write it like that? Yeah, you can. You can write it like that, no problem. Okay, some of you might be wondering, are we always supposed to just put a bracket like this? Actually, you are not supposed to put a bracket like this and show and just finish it off there. If they require the answer in ionic form, you can write it like this and stop. But if they ask you to write the full balanced equation, then you need to write the correct numbers, like I have done here. 4, 3, 2. So basically, we have 4 going here, 3 going here, and 2 going here. You can see 4 iron, 4 iron here, 6 oxygens, 6 oxygens here, all balanced. Is that clear? I feel like before going to naming, we'll do one more question. One more question. I'll take a break after that and we'll start with naming. Naming is just theory, but naming also is something that a lot of students, like, I don't know about how you feel. I know that many students find a bit of a relief after learning about naming, because when they see compounds, they don't know how to name them. Sometimes they feel insecure. You all might be feeling like, how do you name this? Like, what if I get this kind of question? So now you're going to learn all the rules associated with naming. So you will be able to, understand how to name a compound, right? So that's a very, again, important lesson. Right. So write down one last question. We'll call it question number 3. Yeah, on to the same part. Okay, now 1, 2 is done. This is the third one. We did 1. This is the second one. Third one. Magnesium reacts with nitrogen. Actually, this one happens if you burn magnesium in room temperature also, and forms magnesium nitride. Magnesium nitride. Do the same thing we have always done and get to the answers here. Okay everyone, so now we'll start. So over here we have magnesium and nitrogen. Magnesium is 0 in oxidation number. Nitrogen over here is also 0. But magnesium in a compound will add any group 2 element in its compounds will always be plus 2. Any group 2 element in a compound will always be plus 2 oxidation in plus 2 oxidation state. That means nitrogen over here, you can find it out. Let's say if it is X, if nitrogen is X, there are 2 nitrogen, so 2X, so magnesium there are 3 of them, plus 3 into 2 is going to be 0, so 2X plus 6 is 0. That means 2x is equal to minus 6, which is x is equal to minus 3. So we have nitrogen in minus 3 oxidation state. So this is ionic compound, students. So therefore we can write half equations in the following manner. So if you write half equations, we don't write half equations like this. Like, you know, if you can't actually identify different like, you know, oxidation states here, if they are the same on both sides, you can't write a half equation, right? So here we have magnesium turning into magnesium 2 plus, releasing 2 electrons. This is our oxidation. We'll call it reaction number 1. Then we have reduction. So we have reduction, we have nitrogen turning into nitrogen in oxidation minus 3 oxidation state. Sorry, minus 3 oxidation state. So that means 3 minus. So this is called the nitride ion, right? Nitride ion. So I have told you group 1, group 2, group 3, how the oxidation numbers usually change. This is something that I have told you way before this lesson. So, and when it comes to group 5 or group 15, 16, 17, how the oxidation numbers or how their charges will change, right? Group 15 will form minus 3 ions, group 16 will form minus 2 ions, group 17 will form minus 1 ions. So nitrogen has 3 negative charge. That means the nitrogen atom has gained 3 electrons. Nitrogen atom has gained 3 additional electrons. One single atom has gained 3 electrons to form a nitride ion like this. There are 2 nitrogen atoms. Okay, that means how many nitride ions do we form? 2 of these. How many electrons should we gain? Each gains 3. There are 2, so therefore 6. Is that clear? So now this is reaction number 2. So we can very clearly see we need to add 2 and 1, but 1 should be multiplied by what? 1 should be multiplied by what? 3. So we can see, I'll just write it again for your benefit, but you don't have to if you know what the final answer is going to be after writing this. So 1 multiplied by 3 would be 3 magnesiums turning into 3 Mg2 plus, releasing 6 electrons. 6 electrons gained, 6 electrons released. So therefore when you're adding them together, it will be 3 Mg plus 1 N2 turns into 3 Mg2 plus and 2 into so N3 minus, or in other words 3 Mg plus N2 have become Mg3 N2. Mg3 N2. Is that clear? So this is the answer, students. Hopefully you have developed a strong understanding about how to write these type of equations. Okay. So this is the basic intro to redox equations. Very basic one. You will be learning about additional redox reactions and redox reactions balancing in acidic medium, basic medium will be taught to you a bit later once you are comfortable with this. Is that clear? Right. So there are some pages in the TUT, page number 3 and 4. I will get to those next week as a small revision to this, right? That is basically talking about burning hydrocarbons. I'll get to those as a small revision to the questions that I have done here to see whether you actually remember how to do this. Now there we are learning about something called cumulative oxidation number, which is basically addition of all the oxidation numbers in a compound. So we'll learn about that later, right? So we'll have a small break now, and as we start the class I'm going to move on to naming ionic compounds, okay? And then basically we'll learn about overall naming. Hopefully we'll be able to cover a good significant part of naming compounds within the class today, right? So take a small 15-minute break and we'll start the class after that, right everyone? So let's start. Are there more to come back actually? 2 right, either way we'll start now. So now we are going to be talking about naming compounds, ions, molecules. So when it comes to naming, students, now if you turn to page number 5, actually if you read this TUT, you will obtain a very good idea about how the naming works. When it comes to naming ionic compounds, or naming compounds, we'll start with ionic compounds a bit later, but let's learn about naming compounds. When it comes to naming compounds, back in the day we used different names based on the property of the compound we're talking about, right? So, or sometimes like basic names that were used are things like milk of magnesia and then laughing gas. These are like just names that are given based on either appearance or the property, like what kind of chemical properties it has. But as we actually find out more and more different types of compounds, so we can't be just naming everything with a weird name like that, right? Like how many things to remember. So then a union that we currently still have known as IUPAC, International Union of Pure and Applied Chemistry, IUPAC, right? This particular union gave out a way of naming compounds, or naming not just compounds, ions and molecules, everything. So why was there a need for it? Imagine when more and more compounds were being discovered, if in one country they name it one way and in another country they name it another way, it's going to be a problem, right? In biology also you have scientific naming system for animals, just like that. Animals, plants and anything that you find, you have a scientific naming system, right? Anyone who does biology here? Right? Only one student, the other 2 students are not here yet, right? So okay, so just like that, when it comes to compounds also, we want to have uniformity when it comes to naming a compound. So IUPAC naming system gave out a few rules as to how we should name them. So now when naming, let's say when naming compounds, we have mainly 2 different types of compounds. Actually we have categorized for the ease of naming them. One is referred to as organic compounds, organic, the other one is inorganic. So organic compounds are basically the carbon based compounds, carbon based. Mostly, although we say carbon based, it's carbon hydrogen based, carbon bonded to hydrogen. In certain cases organic compounds also have oxygen, nitrogen, phosphorus, sulfur, these kind of things attached to them. So not just always carbon and hydrogen. Mainly the basic structure of the molecules are made up with carbons and hydrogens when it comes to organic compounds. Then there could be sulfur, oxygen, nitrogens attached to it as well. So organic compounds can have all of them, right? So other elements like hydrogen, oxygen, nitrogen, sulfur can be there, right? But the main basic structure of the molecule is made with carbon and hydrogen. Those are referred to as organic compounds. So the naming of organic compounds you will learn under organic chemistry, right? After finishing unit 6 you will be learning about organic chemistry. So there you will learn how to name organic compounds. However, inorganic compounds we will now learn now itself. So I told you organic compounds are basically mainly carbon based. Let me say one thing after that as well. Things like carbon monoxide, carbon dioxide, cyanide, carbonate, bicarbonate, these are not organic. These are, for ease of naming, we have categorized them under inorganic, right? So I told you carbon based, but these are, although we have carbons here, we don't necessarily consider this to be organic substances. They are named under inorganic. Okay, so although we say carbon based compounds are organic and they have a separate naming system, these ones are exceptions. We take it to inorganic. Is that clear? And another thing that you need to keep in mind is, when it comes to inorganic compounds, everything else except for carbon based compounds are referred to as inorganic compounds. Everything else, right? So like ionic compounds, molecules, right? Different types of simple molecules, molecular compounds, everything except for carbon based compounds are going to be coming under inorganic compounds, right? So inorganic naming system. So there are many inorganic substances that we come across, so we have to learn how to name them, right? So the very first thing that you need to understand is, under naming of these compounds, inorganic ones, we have different types. We have ionic, molecular, acids and bases, and hydrates. So we have ionic compounds under this, right, like sodium chloride, potassium chloride, right, magnesium nitride, we learned about it a little while ago, all ionic. And then we have molecules like carbon dioxide, sulfur trioxide, right, we learned about them. And then we have acids like HCl, sulfuric, right, nitric, phosphoric acids. We have bases, right, sodium hydroxide, ammonia, like bases such as those. And then we have hydrates. Now hydrates part in our syllabus is somewhat left out, students, but just to give you an overall idea about naming, I have included hydrates here because it's such a simple thing. But in our syllabus we don't focus a lot about hydrates. We learn about ionic compounds, molecular compounds, and acids and bases. So 3 things. The fourth one is basically, actually acids and bases are not 2 things. Ionic, molecular, acids and bases is just 1 thing, right? And then you have hydrates. I'll teach you about hydrates also. Just quarter of a page is used to teach you about hydrates if you go through the new tude. So it's such a simple thing. I'll teach you about that as well. Okay. When it comes to learning about ionic compounds, now ionic compounds are super easy. Ionic compounds are super easy. Students, can you bear with me just a second? Would you mind if I increase the temperature a bit? I'm feeling a bit cold. Maybe for a while. Okay, we'll turn it off. Not well today, that's why. Okay, so now when it comes to ionic compounds, it's such a simple thing, students. Whenever you are naming ionic compounds, like simple ionic compound like sodium chloride, the cation, or cation means the positively charged ion. Now I'm assuming you already know what a cation and an ion is. Cation means positively charged ion. Anion means negatively charged ion. These are simple things. I think you knew this from O levels. So you identify what is positive, what is negative. So sodium obviously forms +1 charged ions. It's a cation. This is a anion. So when writing names, the name of the cation is written first without any changes to the name of the element. So sodium is when it is forming a +1 charged ion, its name is also going to be the same as the name of the element. So we just write sodium. Is that clear? We just write sodium. If you want to write it as a ion like this, actually since I have just written Na1+, we write it as sodium ion. And then when it comes to negatively charged ion, now there can be many types of negatively charged ion, students. Actually there are mainly two categories. One is monoatomic ions, right? When it comes to both positive and negatively charged ions, there are two main types of ions that you find. Those are referred to as monoatomic ions. That means ions made up of only one atom. Right? Each of these ions are made up of only one atom. No? The other one is polyatomic ions. Poly stands for more than one atom is there in the ion itself. For example, carbonate. Carbonate, this ion is made up of what? Altogether, two different types of atoms, but the total number of atoms is 4. So this is a polyatomic ion. Right? Sulfate, nitrate, all of these are polyatomic ions. You have drawn Lewis structures for these ions, so you are very familiar with this. So this is something called carbonate. It's a polyatomic ions. But when it comes to monoatomic ions, if it is positively charged, you write the name of the element and followed by the word ion. If it is a negatively charged ion, when it comes to monoatomic ions, their name changes. This is usually chlorine, right? But their ending now changes to IDE. Is that clear? Any monoatomic ion has their names ending with IDE. Any monoatomic ion. So this is the positively charged ion's name, negatively charged ion's name. So when you're writing the name of sodium and chlorine together like this, you write the positively charged ion's name first, which is sodium. At that point, don't write sodium ion, okay? We just write the name of the positively charged ion without the ion part in it. And then you leave a space, and then you write the name of the negatively charged ion. So this is the name, sodium chloride. It's the negative charge that has the name slightly changed in it. Right? Negative charge ions, they get their name slightly changed. Okay? So that is the naming of ionic compounds, simple ionic compounds. These are called binary ionic compounds as well. Binary means made up of only two atoms. Bi stands for 2. Right? So these are simpler, very very simple ionic compounds, sodium chloride. So apart from chloride ions, you have to know about other. Now positively charged ions, of course, is easy, right? But negatively charged ions, there's a whole lot to learn about, right? So I told you, when it comes to the periodic table, right, we have group 1, group 2, and then this entire section is basically from group 3 to group 12. Right, you have a section here, these are D block elements, and then we have again group 13 to group 18 here, right, group 13 to 18. So now if I write the groups here, group 1, group 2, and then we name it from group 13, 14, 15, 16, 17, 18. The middle bit is D block elements. We don't talk about them now itself. Right, so I have eliminated that. So now group 1 elements, we know very well they form +1 charged ions. Right, we wrote it in the oxidation states as well. Group 2 elements, +2 charged ions. Right, most of the group 13 elements like aluminium can form +3 charged ions. Okay, now we'll talk about, in your level we mainly talk about the period 2 and period 3. Right, period 2 and period 3. We rarely go below that. When it comes to period 2, period 3, group 13 elements form +3 charged ions. And when it comes to group 14, this is where carbon and silicon is. They can share electrons, so we just write + or -4. They can sometimes form oxidation states of +4 or -4. It depends on the compound they are dealing with. And then when it comes to group 15 forms -3 charged ions in the period 2, period 3, and group 16 -2, and group 17 -1. So group 18 is normal gases. They don't form compounds. They do in certain cases, but we'll say for the time being they don't form compounds, right? Xenon and all that, Xe, can form certain compounds, but for the time being we'll leave it out. So I just want you to see the charges. Group 1 +1, group 2 +2, so that is like fixed, that never changes. And then group 13, elements like aluminium forms +3 charged ions. Group 14, we can't talk about ions that much because they are more likely to share electrons and form covalent compounds. So therefore we write + or -4 because they are more likely to form covalent compounds than ionic compounds. Then group 15, we have -3. We have group 16 -2. And 17 -1. Now I want to focus on these. Group 15 period 2 element is going to be nitrogen. This is oxygen, this is fluorine. So nitrogen forms ions, 3-, oxygen forms oxide ions, fluorine forms F-, fluoride ions. If you take phosphorus, which is also in group 15 in period 3, it forms phosphide ions, sulfur, sulfide, and then chlorine. So these are elements in period 3. Okay, so you need to be familiar with them. Nitrogen forms, the negative charge ions name end with IDEND. So we call it what? Nitride. Phosphorus, phosphide, PHIDE, right? Phosphide ion. This one, oxide, sulfide, fluoride, chloride. Actually group 17, of course, you have to know everyone. Fluoride, chloride, bromide, iodide, acetate, right? So you just have to remember those parts. Is that clear? Right. So now if I give you some compounds, you should be able to tell me the name. Let's see whether you can get the names right. Right. So we learned about this magnesium. What is this? What is the name of this compound? We write the positively charged cation's name first. What is the name of the cation? Magnesium. Oh. What is the name of the anion? Nitride. Is that clear? So what about this N2, not N2 actually, Na. How would you name this? This is the positively charged ion. Sodium always forms +1. So I could have written that also. So sodium, potassium, lithium, always +1. We have, like, magnesium, calcium, these are always +2, right? Beryllium. So beryllium is somewhat has, like, it has different properties. You will learn all about them under unit 6. So, but for the time being, remember these things. So now you write sodium. If you get the spellings wrong, it's going to be a problem, right? Sodium, you write it like this. Now sulfur, some students write it as PHUR or FUR, FER actually. So here when you write sulfide, some students think this is okay. Normally students, under any normal naming system, in general without the UPSC naming system, both are correct. But in the IUPAC naming system, we use FIDE. We use FIDE for sulfur. Otherwise, we can consider both names to be correct. But in the IUPAC naming system, we always use FIDE. So from here onwards, whenever you are referring to sulfur containing species that ends with IDE, you always have to use FIDE, not PHIDE. Okay? So consider this to be wrong. Not that it is wrong when it comes to the common naming system, but IUPAC naming system, we use FIDE. Is that clear? So going forward, always remember that. Is that clear now? I will give you some names. We'll see whether you can get to the answers. Take down a new heading in your writing books. New heading in your writing books. Naming compounds. Then write ionic compounds. Ionic compounds. Now students, I'm not going to give you a separate note there because in the tute, it's a very elaborate detail like that I've given in the tute. So read the tute, underline them. I just want to give you some additional questions and to write down. So write the names of these compounds. I want you to be familiar with writing names of different metal and non-metal ions. So write down the names of these. Do this. Done? Anyone who's done? I believe that's enough time. We'll name it now. So this is called lithium. Leave a space and oxide. Now, one thing to keep in mind is this is not like writing your own name. Your name and your surname. What do you write? Rakhitha, capital R, KALUTHATHRI. Simple K or capital K? Capital K, no? But you wouldn't write it like that when it comes to naming of compounds. Only the first letter is capital, all the other letters are simple. Don't write oxygen here as a capital letter. Is that clear? I see, and another thing, students, when you are writing your formulas also, when I walk around, sometimes I see, like, you know, not at this level, you don't talk about this. When I walk around, sometimes I can't distinguish between this and this. Now, these are two different things. This is carbon monoxide. This is cobalt, right? So be very clear with your simple capital letters. If it is not very clear, you are in, like, you know, trouble, especially at this level. If you don't get it right, it's going to be a major problem, right? So here lithium is written and then followed by oxide. We have magnesium. Remember the spellings. Leave a space. What is this? An iron made up of iodine. What is the name? Iodide. Iodide. IDE should be there. Magnesium iodide. This one, another mistake that a lot of students make. They write potassium like this. POTTASIUM. Wrong. Right? After watching too much of Harry Potter, this can happen. Right? So it is POTASS. POTASS. Not potassium. It is POTASSIUM. Double S is what is important, not T. Potassium. Another one here. PHIDE, right? The whole FIDE part is applicable for sulfur only. Phosphide, don't write with F. Right? Don't ask me why. Right? It's how the naming system works. Right? In English language also, you have so many weird pronunciations and spellings, just like that. Right? So this is called potassium phosphide. Here we use pH. And then we have this is calcium sulfide, FIDE, right? FIDE, and finally sodium nitride. Sodium nitride. Be clear in your handwriting so that you don't make any mistakes. If you write it incorrectly, if your spellings are wrong, then you will lose marks. Is that clear now? Yeah? So although I didn't necessarily talk about carbon forming plus minus 4 ions, carbon can in certain cases form this. Most of the carbon containing compounds are covalent, like 90% of the time, right? So if it ever by any chance form in certain compounds is 4 minus ions, it's called carbide, right? Carbide. Carbon ends with IDE, carbide. This is called silicide. Silicon ending with IDE becomes silicide. So carbide could also mean, now the word carbide is there given for C2 minus as well, right? Actually not just C2 minus, C2 2 minus, right? Like, you know, you say your fruits have been added with carbide, right? That is basically they put calcium carbide to water, then as you, now it's a very simple thing, it's a chemical reaction. If you put calcium carbide to water, it produces a gas called ethylene, right? Or acetylene. So this gas actually can work as a plant hormone, right? It can mimic a plant hormone, if I'm not mistaken. It's the whole biology part of that is not something that I can remember correctly now. But this can ripen the fruit. So you say carbide gahala means that. Is that clear? So when you put carbide to water, the, like, you know, produced gas can artificially ripen the fruit. So it has a very bad taste also, because outside ripe, middle bit not so ripe. Like, that's not how it happens usually. So it's going to be weird. Anyway, so that has this ion. So basically calcium carbide looks like this. Calcium carbide. So this also has the name carbide, right? So we can use the word carbide for both this or this. Actually this is more stable and common than this. Is that clear? This is more commonly seen. Okay, is that clear now? Now apart from that, even now we say monoatomic ions that are negative. We said monoatomic ions, monoatomic anions. Monoatomic anions have the IDE ending. That's what we said. But apart from that, certain other ions like this, OH minus and CN1 minus, these are exceptions. They are also having the IDE ending. Like this is named hydroxide. This is called cyanide. Right? These are exceptions. So these ions also end with IDE, although they are not monoatomic ions. They are polyatomic ions. Their names end with IDE. Is that clear? Right. So after that we are moving on to the next part. Now are we okay with this part now? Yeah? Fine? Simple, right? Not that too complicated. So now we are moving on to the next part. You might have seen certain metal ions having more than one oxidation state. I am sure you would have at least come across a few of these examples. So if you take now the name here, what we are talking about is naming cations with variable oxidation numbers. Okay. Now this is not seen in group 1, group 2 elements. Group 1 elements are always plus 1 only. Group 2 elements only plus 2 only, right? No other oxidation states are possible. But when it comes to like after that we come across group 13, right? Group 3 to group 12. That section of the periodic table is referred to as the D block of elements. You would have seen this, right? We have our S block, and then we have our D block, then we have our P block, right? Group 1, group 2, and then group 3 here, all the way to group 12, group 13, all the way to group 18. Right, so this D block elements also has something called transition metals. So in the D block elements category, there is something called transition metals. These are all things you are going to learn later on. So these elements can have more than one oxidation state, right? For example, I think I'll take something that is somewhat familiar to you. If you take Fe, it can form two different ions, Fe2 plus and Fe3 plus. If you take Fe, these are the two main ions it can form, Fe2 plus and Fe3 plus. Now we have to find a way to name them. Can anyone tell me the name of Fe2 plus ions and Fe3 plus ions? You might already know. What is this called? What is this called? Iron? Or is there a specific name for this? Have you heard of ferrous? Have you heard of ferric? Good. So when it comes to naming these ions, there are two naming systems. Obviously we have the IUPAC naming system, the proper way to name it. And then there is this, the common naming system, which is also referred to as a trivial naming system. Trivial naming system or the common naming system. So that's like the way in which, they have named it before the IUPAC came into action. Is that clear? So the trivial naming system is still stuck. We use it sometimes. Okay? So you need to know. Now you have a name that is officially given to you. What are your official names? You have your official names, right? In your school and all that, you use them. At home, do you ever get called by your correct name? Right? The names you have at home, if I ever get to know about them, it has nothing to do with not even a derivative of your current name, right? So it's like completely weird names are there, right? So I think the parents out of love will call you different names. If they ever call you by your actual name, that means you are in trouble, right? So I have that feeling also. I have had that feeling in your age. So anyway, now what I'm telling you is, when it comes to these names also, the IUPAC names are drastically different to the trivial names, the common names that are given to you. So if I give you the trivial names here, I'll give you the trivial. I'll draw this a bit differently, so it will be easier for me to accommodate both the names. So if I write iron, they can form two different ions. Maybe two separated, bear with me. We have Fe2 plus, Fe3 plus. So the trivial names, I will write in blue. The trivial name is, here is ferrous. This is called ferric. Right? So now do you see the one with the low oxidation number or one with the lower charge ends with OUS, S. One with the high oxidation number or higher charge ends with IC, ik. Is that clear? This one is us, this is ik. So whenever you have different metals forming two different oxidation numbers like that, their names end in that particular manner. Another good example would be cobalt. Right? If you take cobalt, CO, you have CO2 plus and CO3 plus. Now I just told you, when it comes to the trivial naming system, it's like, you know, one with the lower oxidation number ends with us, one with the higher oxidation number ends with ik. Can someone tell me the name of cobalt 2 plus? What is the name? Cobaltus iron. This one will be what? Cobaltic iron. Cobaltic iron. Cobaltus and cobaltic. Is that clear? So we have many like this. Cobaltus, cobaltic. Mercury also have two different oxidation states. So we say mercurous, mercuric. We have lead. Lead is referred to as plumbus, plumbic. Right? We have tin, Sn. Tin is having the symbol Sn. So its Latin root is stannus, like, you know, there's a Latin name for it. The root of the Latin name is taken, and then you put the OUS part and IC part. So we have tin is Sn. So it is actual tin ions are usually referred to as stannous ions and stannic ions. Lead is Pb. So we call them plumbus and plumbic. Is that clear? You need to remember these names, right? You don't need to remember all the different elements and their entire Latin root names, but you need to remember when it comes to this kind of different oxidation numbers, once you need to remember the names, right? So and copper is their cuprous, cupric, likewise. So now over here I have given you the trivial names. The IUPAC naming system is a bit more streamlined, it's easy. So we call this iron, right? Fe is iron, IRON. So we just write the name of the metal within brackets. In Roman capital numerals, we write the oxidation state. Iron, Roman numerals 2 in capital letters, iron. IUPAC naming system is easier. Remembering all of that would be somewhat tough sometimes, but you need to remember all of those because you need to know. Iron to iron. What do you think this is called? Iron within brackets, the oxidation state is 3, right? Iron 3, iron. Is that understood? This one is called what? Cobalt 2 iron, and this one cobalt 3 iron. Is that clear? Simple as that. Okay? All good? Right. So under naming cations with variable oxidation number, take this down. when you're done with this, please tell me. I need to copy down some details. If you're done with FE to FE chart, let me know. I believe you have written the Fe2 plus. Done? Copy this down and start completing it. There's no need to give you as a question. You just understand this is, I just want you to give you a list of names. I want you to write the names as well. I want you to write the name as well. Anyone done? Good. I'm starting in a minute, so quickly write the names. Yeah? Look, I actually told all these names verbally earlier. I'm just wondering whether you caught on to that, like the trivial names. Of course, the UPSC names you can write. The trivial names, if you are struggling, it depends on how much you how much of attention you've been paying here. Right. So let's start. Copper here. So this trivial name is very easy. We'll write the trivial names first, and I'll write the UPSC names. Trivial names here would be cupric, cuprous actually, OUS. I will leave out the iron part. This is cuprous. This is going to be cupric. So it's not copper, copperous and copperic. This is having the bit of a different Latin root to it than what you just write as copper. So it's cuprous, cupric. So here the symbol is SN, so it has a different Latin root. So this is going to be called stannous, NOUS. Stannous, and this is stannic. Stannous, stannic. And we have mercury here, MERCUROUS. This is called mercuric. Right, this one, this is how you write it, right? This is the way in which you write it. Don't try to find out what HG means. We write mercury or mercurous and mercuric. And this is called plumbous ions, and this is plumbic ions, right? Right. There's a small additional N here, students, in sense we have to make that correction. Sorry, I missed out on that. So stannous, N, there's two N's here, STANNOUS, and this is NNIC, stannous, stannic. If you move on to IUPAC naming system, this is called COPPER, copper 1 iron, right? Copper 1 iron. It feels odd to leave the iron part out, so I will write this here, iron. This one is copper 2 iron. Can someone tell me what SN stands for? I just told you earlier when I was explaining. What is it? What does SN stand for? What is it? No, I mean like the name of the metal that you don't usually use stannous, stannic in the IUPAC naming system. What is the name of the metal? Tin, right? Tin. Tin 2, right? Just like for Fe we call iron, right? But their trivial names is ferrospheric. Just like that. Here this is tin 2 iron, and this one is tin 4 iron. This one is mercury itself. So mercury 2 iron. This one is mercury 3 ion. No, 3, sorry students, mercury 1 ion here and mercury 2 ion here. Right? So Hg 2 plus means 1 Hg here is 1 plus. So therefore this is mercury 1. Here Hg 2 plus, that means both the positive charges are on 1 Hg. So therefore this is mercury 2 ion. Lastly we have plumbers. Plumbers means lead, Lead. Lead is the name of the metal that we usually use in IUPAC naming system. So lead 2 ion, and this is lead 4 ion. Lead 2 ion and lead 4 ion. Are we done? So the last part before we wrap it up for today is this. If you are given a compound, you should be able to write both the names, right? So you should not be having any doubts about the name when you're writing the names. For example, if you are given these compounds, FeCl2 or FeCl3 for that matter, right, you should be able to write the names of them. This can have a trivial name as well as a IUPAC name. If I write the trivial names, right, if I write the trivial names, this one will be, can someone tell me what is the name of the cation here? By looking at it you should be able to tell me. What is the name of the cation here? Ferrous. Why? This is -1. There are 2 of them. That means this is +2. So therefore this is ferrous. Leave a space. Now ferrous ion is there along with a negatively charged ion. Always a cation first, then the anion. So ferrous, leave a space, chloride. What will be the name here? Ferric chloride. How hard could it be? Right? So if you're writing the IUPAC naming system, it will be iron within brackets 2, then leave a space. Iron 2 ion was the name that was given in IUPAC. So after that, after naming the cation, you leave a space and then you write chloride. Here also the same. We write iron, the oxidation state of that particular ion, and then leave a space, chloride. Is that clear? Write down a question. We'll wrap it up with a question quickly. Write the names of the following. Write the names of the following compounds. Include both trivial and IUPAC names. Or write both trivial and IUPAC names. Write their names. I want you to write, now I have just written them without leaving any space. for you to write the name. So you take them down and write their names underneath or to the side. I don't mind, but write the names of these four compounds. Very good. If you're done. These days it gets dark really fast, right? It's now pitch black outside. Okay, I think it's time to discuss. So let's see, before we start discussing, we need to find the oxidation number on each of these. Oxygen is -2 always, right, in compounds. So copper over here, there are 2 of them, right? So if you find the oxidation state of copper using the methods that we have discussed in the previous parts, you will see copper is going to be having +1 oxidation state. Right, you can find it, and then you get to the answer. The trivial name will be cuprous oxide. Cation's name is cuprous because it's +1 oxidation state. Anion is oxide. Oxygen as a negative ion will be oxide. IUPAC naming system will be copper, 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 space, and then oxide. Oh, copper, before we write the space oxide part, copper we write the oxidation state and then oxide. Copper 1 oxide. Then we have SN, Cl4. Again, Cl is -1, most of the time. So in this case it is connected to a metal, which is metals are having very low electronegativity, so therefore definitely chlorine is -1 here. So if you find the oxidation state of SN, it will be +4. So therefore what we are dealing with here is stannic, NNIC, STANNIC, stannic, leave a space, chloride. This is the trivial name, common name, right? And then when it comes to the IUPAC name, it will be tin, within brackets 4, then we have chloride, tin 4 chloride. Don't leave a space between tin and 4 like I have here. I didn't intentionally keep it. Actually there shouldn't be any other space in the entire name. The only space that you should find is between the two names. Tin and 4 can't have a space between them, okay? Tin 4 chloride. And then we have Hg2Cl2. I told you Hg2Cl2. Now whenever you see this Hg2 part, it could be Hg2 2+, mercurous ion. I gave you the formula earlier. So therefore, anyway, if you find the oxidation state of both of them, you will see this Hg is in +1 oxidation state. So therefore, trivial name would be mercurous chloride. IUPAC name would be mercury 1 chloride. Mercury 1 chloride. And finally we have, anyone can tell me the oxidation state of sulfur and Pb here? Can someone tell me the oxidation state of Pb here? Is it +2? Is it +2? +3? +4? Yes, it's +4. This is sulfur forms 2 minus ions, so therefore oxidation state of sulfur is -2, right? And this will be +4 because 2 sulfide ions are there attached to it. 2 sulfides mean definitely here lead is in +4 oxidation state. So the name would be plumbic sulfide. This is trivial name. IUPAC name is lead 4 sulfide. Lead 4 sulfide. Is that clear? So whenever you are writing names, keep that in mind, students. Spellings are important, especially like in the previous case I told you, if you miss an N here you lose a mark, so don't miss that N. And apart from that, copper also, when you're writing IUPAC naming copper, 2 P's. When you're writing trivial name, it's only 1 P. Okay, keep these things in mind. Is this clear now, everyone? 100% okay? Brilliant. So we'll wrap it up for today. Next week we are starting with naming system of covalent compounds, and then we move on to oxo and ions and basic acids and bases naming system. Alright, so that will be all for today. I'll see you again next week. Have a good night, everyone.